Hi there and welcome to our lesson 3 in our P6 topic of logic gates. Now we are looking at both simple logic gates, and then we're going to move on to have a look at some very complex logic gates and how they can be used in electrical systems such as bank vaults and lifts or cars to give us an input, or use the input to provide an output for a particular electronic device. Anyway, I hope you enjoy it, and I'll see you at the end. Bye-bye. Okay, so here are our objectives today on logic gates. So by the end of this lesson, you should know and understand how logic gates can be used in an electrical system to decide the output of the system. Now we'll be looking at 5 logic gates: a NOT gate, an AND gate, an OR gate, and then when we put a NOT with an AND, we get a NAND, and a NOT with an OR, we get a NOR gate. Anyway, I hope you enjoy it, and I'll see you again at the end. Okay, so let's have a look at what logic gates are able to do. So first and foremost, we can see that logic gates allow electrical systems to make decisions to turn on or off part of a circuit. So it relies on an input to be able to supply an output. Now, if we have an input to a logic gate, it can be a high voltage, which is about 5 volts, known as high, or it can be known as 1. And then you can have a low input, or low voltage, which is nearer to 0, and that is known as 0 or low or 0. Now the output is then going to be high or low depending on what the input signal or signals are. Now it could be that you have switches, LDRs or thermistors which can go into the inputs for the logic gates to provide the output. Now then, adding this to the potential dividers that we looked at previously, we can then get a low or a high voltage input. So for example, if you've got the thermistor that will change the resistance in the R2 of the potential divider, then that will change the output. Now the first logic gate we're going to look at is what we call a NOT gate. Now the NOT gate has an input here which goes into the NOT gate, and we get the output here, which is labelled as Q. Now NOT means it's exactly the opposite of what the input will be. So Q will be the opposite of what A is. So if we have a high input, we'll have a low output. So we'll have a high voltage going in, a low voltage coming out. And then if we've got a low voltage going in, we'll get a high voltage coming out. Now an AND gate is the second type. Now this is similar to having 2 series switches in a normal circuit. Now what we have is we have 2 inputs, input A and input B, and again we have our output Q. Now what we need is we need to have inputs A and B both high to be able to get a high output. So if we have 2 low inputs, because they're both the same, we'll have a low output. And again, we've got a low and a high. Now it's not A and B, it's one or the other, so we get a low output. Now AND gates can be used for things like a lift, where you need to have the door closed to give a positive signal and the button pressed in order for the output of the lift to move. Now an OR gate is where you can have 2 inputs and you can have one or the other to give you your high output. So here it's like having 2 switches in series going into a circuit. So it doesn't matter whether you have this light switch on, the light will come on, or this switch, the light will come on. So if we have 2 low inputs here and here, you'll get a low output, whereas if you have one, either A or B as high, that we can see here, and for both here the outputs will be high as well. Now, following on from the AND gate and the NOT gate, if you join them together you make a NAND. Now this means not AND. Now what it means is that if you have a low and a low, you end up with a high. So A and B are low, so you get the opposite. And with A and B, if one is low and one is high, you get the opposite. And one is high, one is low, you get the opposite, which is high, because you haven't got the AND, it's not AND. And then when you do have high and high, you end up with the opposite low. And the last logic gate that we'll look at is the NOR gate. Now NOR is the not OR gate, so it's not an OR gate, it's exactly the opposite. So where we have the three highs as the options for the output here, this means that you have a low and a low gives you a high, rather than having the one or the other to give you your high. Now here we've got a AND gate added into a potential divider. Now our R2 here, our second resistor, is what we call a thermistor, and we've got a fixed resistor at the top here. Now, as we've seen with our potential dividers, when you change the resistance here, it can change the output here. So this might be for a potential divider going to a heater through our logic gate. Now, if the temperature drops on our thermistor, then we have a high resistance. Now, when we have the high resistance, the input to the thermostat will be high. Now, because we've got two highs, because this will be a fixed high, and a high going in here, we then have the heater turning on. Now, after a while, the heater turns the room a bit warmer, so our thermistor causes the temperature to increase. This means that we have a lower resistance, and therefore our AND gate, or this entrance, the B entrance to our AND gate, will be low, meaning that we have only one input, so this will turn the heater off. Now, in exactly the same way, we've got an LDR, which is a light dependent resistor. Now, as the light shines in, you have a low resistance. So when the light level drops, the resistance increases, meaning that out of here we'll have a high input. Again, with our fixed high input here, means you've got A as a high and you've got B as a high, meaning that you can turn the light on. Now this is where we get to some quite complex truth tables. Now here at the bottom, this is what we call our truth table. Now we've got our inputs A, B and C. A, B and C. Now for A, it can either be off or low or 0, or it can be on or high or 1. And it's the same for B as well. Now we've got an AND gate and an OR gate. Now with the AND gate you can work out what D will be. So for example, if A and B are 0, D will be 0. Whereas if it's 1 and 1, this will be a value of 1. Now D and C go into our OR gate here. Now that can then be used to work out what Q will be. So let's have a look at what the truth table will show us. So as we go through, we can see that for the AND gate, it's only the bottom two where we have both A and B on that we get our input for D being on. Now because this is an OR gate in here, it means it can be C or D that turns it on. So here we've got D and C both off, so we get no output. Whereas when C is on, we get an output. When C is on here, we get an output. And then again, it's every other one except for the bottom one here, where we have both in, and that means it turns on. So as we go through, we can see that for the AND gate, it's only the bottom two where we have both A and B on that we get our input for D being on. Now because this is an OR gate in here, it means it can be C or D that turns it on. So here we've got D and C both off, so we get no output. Whereas when C is on, we get an output. When C is on here, we get an output. And then again, it's every other one except for the bottom one here, where we have both in, and that means it turns on. So here we've got a very complex set of logic gates. Now here we've got a OR gate, and we've got an AND gate, and then we've got a NOR gate. So what we need is either A or B to go in to give us an input to here. And then we've got C and D are needed to give us an input to here. So E relies on A and B, F relies on C and D, and therefore Q will rely on E and F. So let's have a look at the truth tables for this one. So if we have a look, A and B contribute to E, so this is what we find, that these are the codes that we get, so it's either A or B. So when we get a 1 in any of these columns, we'll have a 1 in the E column. So we need just one of A or B. So when we add in C and D, you need to have C and D to give us an output for this one here. So here we've got C and to get our outputs for F, and then we just use E and F to get our Q. So because it's a NOR gate, you need neither E and F to give us an output. So whenever it's 0 or 0, we get a positive output. So whenever we get an input from E or F, it means that we get no output at all. Okay, so we have looked at the NAND gate, the NOR gate, the NOT gate, the NAND and the NOR gates as well. Now the key thing is to look at the logic tables and look at how they work, meaning that if it's an AND gate, you need A and B to give you that Q out. Now with the more complex ones, it's worthwhile being methodical about how you actually go through and work out what the output will actually be. And for some of those, it can be some quite complex electrical systems, such as bank vaults and the like. Anyway, I hope you've enjoyed this, and I will see you next time. Take care. Bye bye.